Hello, my name is Junsu. I present our paper, PinK High-Speed and Storage Key Value Store with bounded details. DGIST and MIT collaborated on this work. Key value store has become an essential infrastructure in many applications, such as web indexing, caching, and storage systems. Many key value stores have been developed, and the academia has researched key value store in various ways. Applications that use key value stores are usually based on host system key value engines. These engines use block-based SSDs as the storage device. Another approach is to use the key value SSD, which is called KV-SSD. KV-SSD is a new storage device that provides key value functionality in the SSD. Using this decreases the latency of the host system and produces high throughput with fewer host resources. Also, it is easy to exploit special resources such as capacitors and accelerators. Many research on KV-SSDs have been done in the academia. Industry like Samsung are also interested in KV-SSDs. However, there are two challenges in implementing KV-SSDs. First of all, the DRAM resources in the SSD is very limited. The SSD usually has DRAM as much as 0.1% of the total capacity for indexing. The problem is that the indexing granularity is 4 kilobyte, which is bigger than the average key value size, which is 1 kilobyte. It means that the SSD's DRAM capacity for 4 kilobyte indexing is not enough to index key value pairs. Furthermore, since DRAM scales slower than NAND, this problem will become worse. Secondly, CPU performance is limited. To reduce power consumption, SSDs uses lower power processor like ARM CPU instead of x86 CPUs. Given these two limitations, which algorithm is better for KV-SSDs, hash or LSM-tree? To evaluate hash-based KV-SSD, we tested Samsung's KV-SSD's prototype. The benchmark used is KB bench with 32-byte key and 1 kilobyte value read request. To compare the performance, we also evaluated the block SSD with FIO with 1 kilobyte read requests. The block SSD showed consistent performance no matter how much data are stored in the device. However, hash-based key value SSD showed inconsistent performance. The more data stored, the lower the throughput and the slower the latency. What causes this performance drop? To figure out the cause, we took a deeper look at the hash algorithm of the hash-based KV-SSD. In the hash algorithm, there are two ways of constituting the hash buckets. One way is to populate an entry with a full key and a pointer to the value. The other way is to use an entry with the signature of the full key and a pointer to the key value pair. When the size of the SSD is 4 terabyte, the DRAM size is 4 gigabyte. When the device stores 32-byte key and 1 kilobyte value, the total size of the hash buckets are 144 gigabyte and 24 gigabyte respectively. Due to the huge size of hash buckets with full keys, we use buckets with signatures as many others do. Since the hash buckets are too large to be stored in the DRAM, instead, all the buckets are stored in the flash and some are cached in the DRAM. For example, there is a GET request for key 7. Its signature is 1000 and the bucket number is 10. However, bucket number 10 is not in the cache, so it is read from the flash. We can get the value of key 7 from the bucket entry. However, in some cases, signature collision can occur where different keys having the same signature. To resolve this, the hash has to prove other key value pairs, which increases the number of flash accesses. The hash bucket leads due to the cache misses make the performance drop, and resolving signature collisions leads to long tail latency. Another approach is to use LSM-tree. Since LSM-tree is sorted structure, it has lower DRAM requirement, collisions do not occur, and it is easy to solve range query. However, is the LSM-tree really good enough? The first problem of LSM-tree-based KV-SSD is the long tail latency. LSM-tree adopts Bloom filter to improve the gap performance in the level. To retrieve a key value pair, it first checks level 0. If the target key is not found in level 0, it moves on to the next level. Before searching the indices of level 1, the existence of the target key in the level is checked by the Bloom filter. If the key passes the membership checking, the flash is accessed to retrieve the value. However, even if the membership checking has been passed, the level may not contain the target key value when a false positive occurs. The same process is done for the subsequent levels until the target key is found. Therefore, the worst case number of flash accesses to get a single key value pair equals to the height of the LSM tree. The second problem is the CPU overhead. The LSM tree performs merge sort during the compactioning of two adjacent levels. In this process, a new Bloom filter is also constructed. The SSD's ARM CPU spends a lot of time in sorting during compaction and building the Bloom filters. The last problem is the I/O overhead. Lots of flash accesses occur during a compaction. We evaluated the LSM-tree-based KV-SSD to verify the problems. The tested KV-SSD is RiceStore, which was presented at ASPLOS 2019. RiceStore is based on key value separated LSM-tree and Bloom filter. To make it clear, we changed the Bloom filter to the state-of-the-art Bloom filter suggested in Monkey. We use YCSB-Load and YCSB-C benchmark for write and read tests respectively. In YCSB-Load, most of the IOs account for the LSM-tree's compaction process. However, when you break down the time taken for compaction, the time took for Compaction IO is quite small. The majority of the compaction time was taken up by the Bloom filter building process. Also, the time taken to sort during compaction is not small. As the results show, the LSM-tree's CPU overhead is problematic for KV-SSDs like Compaction IO overhead is. When you look at the latency of YCSB-C, although RiceStore is using the state-of-the-art Bloom filter, we can see that it has a long tail latency. The PinK is a new LSM-tree-based KV-SSD which resolves problems that are mentioned previously. The long tail latency problem is resolved by level pinning, which is storing the top several levels of LSM-tree in the DRAM. The CPU overhead is resolved by removing the Bloom filter and adopting hardware accelerator for compaction. The I/O overhead can be dealt with the level pinning technique, which can reduce compaction IOs. Also, PinK further reduces the IOs by reinserting the valid data to the LSM-tree on SSD's garbage collection. Now let's look into the details of PinK. The LSM-tree used by PinK is based on the key value separation technique. All keys in the flash are stored as the form of a data structure called meta-segments. The entry of the meta-segments consists of key and the pointer to the corresponding key value pair. The set of key value pairs stored in other flash area are called data segments. The two types of segments are stored in the flash exclusively. The level lists are maintained in the DRAM to index the meta-segments. Level list exists for each level and also sorted arrays. The entry of a level list has the start key of its meta segment and the address pointer, which is the address of the meta segment. The level 0 is a scheme list which stores the keys and the values. Let's look at an example of the get operation in the LSM-tree. Suppose an LSM-tree has 5 levels, except for level 0. The LSM-tree has 4 level lists and 4 sets of meta segments. To improve the gap performance, it adopts the Bloom filter like conventional LSM-tree. Then, first of all, check the existence of the key by using the Bloom filter. Then it finds the target address of the meta segments in the level list. By reading the meta segments, the address of the target key value pair could be retrieved. With a level list with many entries, the meta segment which may hold the target key is found using binary search. This process goes on until the target key value pair is found. As mentioned in the introduction, the flash is to be accessed for all the levels of the LSM tree except level 0. Therefore, PinK does not use Bloom filter. Instead, PinK uses level pinning technique, which pins all the meta segments of the top several levels in the remaining DRAM space. In this case, the get operation accesses DRAM rather than flash when the level is pinned. Level pinning makes the worst case cost of get operation as one flash access. Some may think that it requires a lot of memory, but it does not. Let's assume the same environment used in calculating the hash memory usage. About 8 MB is assigned to PinK's level 0 to exploit the parallelism of flash. When PinK has 5 levels, the total memory usage of levelist is 432 MB. Depending on the number of pinned levels, the memory usage are like these. To fit in the 4 GB DRAM, PinK pins the top 3 levels in DRAM. In this case, 3.5 GB is required, which is smaller than 4 GB. PinK can bound the read cost to one flash access with less than 4 GB memory usage. The PinK's get operation flow requires many binary search operations. Now we will calculate the search cost. Suppose there are H levels in the LSM tree. The size of the rebel increases by the T times as the rebel increases. The search cost of this LSM tree is OH squared log T. The ARM CPU considers these costs are burdensome. To optimize this, PinK borrowed the idea from a fractional cascading. The range pointer is added to each entry of the rebel list except for the last level. With the range pointer, the binary search of level 1 is same. But from the next level, by using the range pointer, the range of search can be reduced as only the level list entries of the overlapping range. Consequently, this reduces the search overhead to OH log T. PinK can reduce search overhead further by using prefix array. Before searching level list to find the full key, the prefix array is searched first. This makes the binary search CPU efficient. If the two prefixes have the same value, then the level list is searched. These two optimizations only requires 10% of memory used in level GIST. Another effect of level pinning is reducing compaction I/O overhead. First, let's have a look at the compaction process when PinK does not use level pinning. When a level becomes full, it leaves the meta segments of the full level and the level below. After it sorts two sets of meta segments, the resulting meta segments are written to flash, and the level list is updated. During this process, it takes 6 reads and 6 writes. Let's consider the level pinning case. Since the target meta segments already exist in the DRAM, it just sorts the data and stores the new meta segments in the DRAM. These newly made meta segments can be protected by capacitor in SSD. After that, the level list is updated and the compaction is finished. The compaction process does not include any flash accesses. However, the CPU overhead of sorting still exists. To reduce CPU time during compaction, we implemented the sorting process with FPGA. PinK informs the accelerator the meta segments of the two rebels and several flash addresses where the new meta segments will be stored. The FPGA leads flash or DRAM by the address of the meta segments and then sorts them by simple key comparison logics. It writes newly created meta segments to DRAM or flash. Finally, the FPGA transfers the resulting level list back to PinK to update the LSM tree. The PinK we presented removes the Bloom filter, which has a lot of CPU overhead and causes long tail latency. By using level pinning instead of Bloom filter, PinK can bound the tail latency and reduce compaction I. Also, it optimizes search overhead and adopts hardware accelerator for compaction to reduce CPU overhead. Please refer to the paper for the explanation on reducing the IOs in garbage collection. Now I show the performance of PinK. All tested algorithms were implemented on Xilinx GCU 102 evaluation board. This board has ARM processor to run KV-SSD's algorithm and FPGA to implement hardware module. We attached a custom flash card with 256 GB of raw NAND chips. The client-server learning benchmark has these specifications. All the requests will be sent to custom KV-SSD by 10 GB Ethernet network. For fast experiments, we scaled down the flash card and DRAM to 64 GB and 64 MB respectively. We used YCSB's core workload for benchmarking. The experiments are run in 2 pages. In load phase, 44 million uniquely random requests are put into the KV-SSD. In run phase, KV-SSD processes the requests generated by one of the provided YCSB workloads. We evaluated hash and LSM-tree algorithm for comparing PinK. Since Samsung KV-SSDs is a black box, we implemented hash-based KV-SSD using 8-bit signature key. We use light store implementation for the conventional LSM-tree, who has total 5 levels. PinK has total 5 levels and top 3 levels are pinned in DRAM. Thus, only 1 level resides in flash. We also tested PinK with hardware accelerator to check the effect of the accelerator. All types of KV-SSDs used same 64 MB DRAM. Hash used the RDRAM for cache, LSM-tree assigned DRAM to level lists and bloom filters. PinK and PinK hardware assigned DRAM to level lists including prefix and range pointer. The remaining DRAM was assigned to level pinning. Let's analyze the throughput of each KV-SSD implementation. PinK hardware has 37% and 44% improved performance than hash and LSM-tree on average respectively. Since PinK hardware removes bloom filter, which is a burden to CPU, and adopts hardware accelerator for compaction, it has at most 156% improved performance than LSM-tree. Also, PinK hardware has at most 21% improved performance than PinK, which does not use hardware accelerators. In the case of workload C, PinK has a little bit lower performance than hash. Because PinK does not have the cache structure, it cannot utilize lead locality of workload. PinK also has slightly lower performance than LSM-tree since LSM-tree can skip binary search by bloom filter. On this slide, we compare the latency characteristic using YCSB. As it suffers from signature collisions, it has the slowest latency. Although LSM-tree uses state-of-the-art monkey bloom filter, it still has a quite long latency. However, in the case of PinK, it shows the shortest latency since it can bound lead operation. This slide shows the effect of using level pinning. The left graph shows the number of flash leads per query. Hash should access flash while processing set operation for checking collision. Thus, PinK has better results than hash in almost all cases. For YCSB-C, which is lead-only workload, hash accesses flash slightly fewer than PinK due to the cache structure. But PinK always performs get operation with fewer flash accesses than LSM-tree by level pinning. The right graph illustrates the ratio of compaction I/O out of total I/O. PinK does not issue read and write requests to flash when it compacts pinned levels, so the ratio of PinK is much smaller than LSM-tree. To evaluate the effect of search optimization, we compare the PinK and unoptimized PinK against the LSM-tree. The YCSB-Load and C are used for this evaluation. In the YCSB-Load, PinK shows slightly lower throughput than unoptimized PinK due to the overhead for creating prefix and range pointer. However, in the YCSB-C, the read workload, PinK have a lot of improvement than unoptimized one. LSM-tree can skip binary searches using Bloom filters, and thus it shows slightly better throughput than PinK. However, Bloom filters cannot bound the tail latency, so PinK has better latency characteristics. The LSM-tree algorithm has good write performance in a Torah tree, but the Torah LSM-tree needs more DRAM to bound lead to 1+ access. To know the read performance when DRAM is not enough to pin sufficient levels, we evaluate LSM-tree and PinK as the number of levels changing from 4 to 8. LSM-tree shows that 2 flash accesses is needed per query on average. But the tail latency of LSM-tree degrades more as increasing the total levels. In the case of PinK, it needs more flash accesses per query than LSM-tree on average. But the tail latency of PinK is almost eliminated. In conclusion, the conventional KV-SSD's algorithm have performance degradation since they did not consider the limitation of embedded systems. The PinK we presented is a new LSM-tree-based KV-SSD which resolved the problems. To reduce long-tail latency, PinK uses level pinning which pins KV indices of the top levels of LSM-tree in DRAM. Also, PinK adopts hardware accelerator for reducing CPU overhead of sorting in compaction. Additionally, it suggests several optimization of LSM-tree-based KV-SSD. As a result, PinK shows the 73% and 42% improved latency performance at 99 percentile latency and average latency respectively. Also, PinK's throughput is 37% higher than conventional algorithms. Thank you for listening to my talk. Please send me an email with any questions.